morning, students. In the last class, we were solving one question related to right hand thumb rule, that is nothing but example 13.1 question, which you understood clearly. But look here, in the textbook we also have the solution. We'll try to analyze the answer what they are given in the solution in textbook. Okay, so this is also easy, so better we'll go with this answer rather than in yesterday's video. Okay, so here we need to find out the direction of magnetic field lines based on whatever the question they are given. So let us see what happens to the direction of magnetic field in clockwise and anti-clockwise direction. So here you know that current is flowing from east to west, so let us see about the direction of magnetic field from west side and east side. For better understanding, along with the video, use your right hand and do it as the instruction given in this video. Clear? So take your right hand and just mark your or just assume that your thumb is showing the west direction and our opposite side will be east, because current is moving from east to west, and you know that curls of fingers are nothing but they are showing the magnetic field direction, right? So here you can observe that when you look from west side, what happens? The magnetic field lines are moving anti-clockwise. So similarly, look from east side, on either side, on another side of your hand. So look from that side and you can also observe that the magnetic field lines are moving clockwise. So this is what the answer given in your textbook, that is nothing but the current is in the east-west direction. Applying the right hand thumb rule, we get the magnetic field turns clockwise when we viewed from the east end, and also anti-clockwise when we viewed from the west end. Okay, so we'll go with this answer, and what we discussed in the last class, that is nothing but north to south and south to north. So even if you analyze that answer also in depth, you are able to get the same answer, that is nothing but clockwise and anti-clockwise from the west and east direction.
In today's class, let us see magnetic field due to current through a circular loop. In the last class we studied under straight conductor or straight wire. Today we will see under circular loop and solenoid. I'll come to that when we finish this one. And this is the second one. The first one is straight conductor. Okay. See, observe here, circular loop. Last class what we studied? Straight conductor or straight wire, something we have like this. So circular loop is nothing but if we bend this wire, if we bend this conductor in such a way, we will get circular loop. Okay, just we need to bend, and these are the terminals because we need to connect these two to circuit diagram, right? So circular loop is nothing but bending this straight wire, we will get like circular loop. Later on, we need to drag these two in terminals so that it will be easy for us to connect to the rest of the circuit devices. So first let us understand through an activity. Later on we will observe how exactly it will work. Okay, concentrate and try to understand each and every point. See here, let us understand through an activity. As we took earlier a rectangular cardboard sheet, here also we need to take a rectangular cardboard sheet just like this, and here we need to make two holes. In the rectangular cardboard sheet, we need to make two holes to pass the circular loop of an wire. See, we have wire like this, right? Circular loop. So we have one terminal which was passing in one hole. Later on we need to make number of circular loops using the copper wire of or whatever we are taking the conductor. Later on, another end we need to take out from this hole on the cardboard sheet. Okay, take this and see, these two are these terminal wires of this copper wire. Later on, these two wires should be connected in the circuit with the device, battery and key. So now what we need to do, next step is sprinkle the iron fillings on this cardboard sheet. So now we have sprinkled many irons fillings on this cardboard sheet. Later pass the electricity and just tap gently on the cardboard sheet. Now we will see how magnetic field lines produce near this wire. Okay. So just to understand, let us take any 2 points like this end and this end. of the copper sheet. So we'll get what? Pattern of magnetic field, and just let us understand through this video how it exactly works. Okay, watch the video and understand carefully.
Look at this video. Everything is set up inside the glass slab, that is iron fillings and copper wire as a circular loop has been set up. When we pass the electric current through this, it goes through the loop and generate magnetic field lines. Now observe carefully, we are getting the pattern of magnetic field lines. The iron fillings are arranging themselves and reveal the pattern to us. And observe here, the concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire. By the time we reach at the center of the circular loop, the arcs of this big circle would appear as a straight line. Observe in between the wire, we can observe those arcs as a straight lines. Those magnetic field lines will look like this. Observe the diagram. See, the two terminals of a copper wire is connected to a circuit, that is to the battery. Observe the positive and negative terminal of a battery. Current flows from positive terminal to negative terminal, right? So here current is flowing from down to up, and we need to find out the magnetic field direction where the concentric circles are produced using right hand thumb rule. Now I will take one concentric circle and explain you using right hand thumb rule the direction of magnetic field lines. Listen and understand carefully. Now here is our copper circle, which is almost similar to that loop. Current is flowing in this direction. Now we need to find magnetic field direction on everywhere of this circular loop. In last class, we saw for straight wire, we can find direction of magnetic field using right hand thumb rule. Right, here also we use the same technique. Just recall what we studied about right hand thumb rule in the earlier class. That is, thumb points towards current and the circular fingers that shows the direction of magnetic field, right? Now let us take sides of circle to find. We are chosen this because it is easy to draw magnetic field lines, and same procedure apply for all the spots of a circle. Now let us see how we will get the direction of magnetic field when we apply right hand thumb rule at the sides of the circle. Look at this diagram. It shows the magnetic field direction using right hand thumb rule. See how we hold the circle in our hand. That is, a thumb is showing direction of current and the fingertips are showing the direction of magnetic field. In the similar way, we'll do on another side of the circle. So here also, using right hand thumb rule, we get the direction of magnetic field lines. In the first case, we observed that it is in clockwise direction, whereas now it is in anti-clockwise direction. Now observe the direction of magnetic field lines inside and outside the copper wire circular loop. See, we can observe that the magnetic field inside the loop is pointing upwards and outside the loop it's pointing downwards, and this will apply throughout all the spots of the circle. So let us recall, inside the loop it is pointing upwards, and outside the loop it is pointing downwards. Now let us imagine the complete picture. Look at all the field lines. Inside loop, the direction of magnetic field is upwards, and outside it is downwards. Now, is this picture familiar to us? Observe carefully and think. Yes, of course, it is similar to field lines of bar magnet, right? Imagine the field lines, how we got around the bar magnet. They almost look similar. If our bar magnet is small, that is tiny bar magnet, we get almost same picture, and therefore if we think of bar magnet with the poles, we can name this as north and south pole.
Here I just enlarged this particular part to understand in better way. So this is how magnetic field produced around the circular loop, and we have two ends, and we know what are the direction and what are the outward direction and what are the inward direction. Okay, understand this? And see, observe here, as the circles are getting larger, they are making the arc somehow in a straight manner. When it keeps on going, these circle shaped arc was enlarging themselves, and they will become somewhere like a straight product, and that is here I am showing as in north and south. Hence, from this activity or from this experiment, we learned that in a circular loop, it can be represented by concentric circles at every point where the magnetic field is produced, and circles become larger and larger when they move away from the wire. And the direction of magnetic field inside the loop is same in all the directions. So inside the loop we will get same direction of magnetic field, and every point on wire carrying current would give rise to magnetic field appearing as straight line at the center of the loop. So we just took an example for two sides of the wire to show the magnetic field, but it will give the same thing wherever we spot on that wire, and finally it will appear as a straight line at the center of the loop. So these are the main points which we learned under magnetic field due to a current through a circular loop.
Factors affecting magnetic field of a circular current carrying conductor. See, there are 4 factors. The first one is magnetic field is directly proportional to current passing through the conductor. This means if current in the wire is increased, the deflection also increases. That is nothing but magnetic field will be more. Hence, it is directly proportional to current passing through the conductor. And the next one is magnetic field is inversely proportional to distance from conductor. If the compass is placed away from the wire, then we can observe that the deflection in the needle decreases. That means magnetic field strength is weaker away from the wire. Therefore, magnetic field is inversely proportional to distance from the conductor. And the next point is magnetic field is directly proportional to number of turns in the coil. This means if we have more number of coils of a wire, then magnetic field will be produced more. Therefore, the number of turns of the coil is more, then automatically magnetic field will also increases. And the last point is magnetic field is additive in nature. Magnetic field is additive in nature. See, magnetic field of one loop adds up to magnetic field of another loop. See, the earlier point I told that if if the number of turns are more, then magnetic field will be more. So here what happens, the magnetic field of one loop, that is for the first loop, will adds up to the magnetic field of another loop, and it keeps on adding magnetic field of one loop to magnetic field of another loops. Therefore magnetic field is additive in nature, and we know that this happens because the current in each circular turn has same direction. When the magnetic coil makes the shape of circular coil, what happens, it will have same properties of single coil, right? Therefore the current in each circular turn will be in same direction. Last class we studied magnetic field lines in straight conductor and circular loop. In today's class, let us see magnetic field due to current in solenoid. Now we got new term, that is solenoid. Let us see what is solenoid. We know that using straight conductor we can make a circular loop. Now using that circular loop, or using that straight conductor, we can make number of loops by turning them again and again. Then we will get like this, which is in the form of coil. This is nothing but solenoid. Hence solenoid is nothing but a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder. You can imagine spring in our ballpoint pens, which looks exactly same. Today's class, let us see what happens when we pass electricity to this solenoid, which type of or which pattern of magnetic field will produce. See, solenoid, here solen means pipe, oid means shape, so which is in the form of pipe shape, that is nothing but cylindrical shape. Now see, this is our solenoid which have number of turns. When we connect to these terminals a battery, we will get a circuit like this. Now when we pass the current, we will get what? Magnetic field lines. That we need to see how we will get. First just to consider this first loop. It is exactly same as circular loop. How we got there? We got number of concentric circles at the inside, and the same thing will happen at every spot, right? So here also we'll consider this end and this end because it will be easy to write. So in the same way we will get what? Concentric circles at the insides like this, and again this end also same thing happens. So when we pass the electricity, we will get concentric circles right. Just imagine circular loop. What happens? We are getting arcs when the circles larger and larger. We are getting like this, right? Which are almost looking like a straight lines in one single circular loop. But here what happens, when these magnetic fields forms, in between the solenoid we will get number of straight lines which are parallel to one another. Parallel to one another. Later they are almost in the form of arcs only, but in between the solenoid, just observe from here to here, they are almost straight, which are parallel to one another, and they are uniform. So observe, in between the solenoid we will get parallel and uniform lines. So let us consider south and this one be north. We know that magnetic field flow from north to south, right? Look at the direction important, you need to mark them, and same thing happens below also. Now observe what happens inside the solenoid. When this comes like this, inside the solenoid magnetic field will flow from south to north. Okay, so these are the direction inside the solenoid, south to north, outside the solenoid, north to south. Observe the video. Inside the coil, that is solenoid, we are taken soft iron here and we are sprinkling iron fillings around the solenoid on a cardboard sheet, and the terminals are connected to a battery. Now just by tapping that cardboard sheet, just observe the magnetic field lines are getting exactly similar to the magnetic field lines in bar magnet. So watch properly, understand. Both are similar. That is, magnetic field lines are similar in both solenoid and bar magnet. Now observe this. We are just concentrating inside the solenoid here. Here current has been already passed. And see, inside the solenoid we are getting uniform parallel magnetic field lines. The main points which we need to learn from this topic under the solenoid are: a coil of many circular turns of insulated copper wire wrapped closely in a cylindrical form, which is called as solenoid. This is our first point. And the second point is magnetic field of a solenoid is similar to that of a bar magnet, which we just learned by looking to the diagrams. And the third point is magnetic field is uniform inside the solenoid and represented by parallel field lines. See, this third point is very much important. They may ask you 1 marks question that in which magnetic field lines will observe uniformity, that is nothing but in solenoid, and which are represented as a parallel field lines. So mark this third point as a important. You need to remember both the words uniform and parallel. Underline these two words. And the next point is solenoid can be used to magnetize a magnetic material like soft iron, or to increase the strength of magnetic field, soft iron core is used. This point explains that for the better magnetic field lines we use iron inside the solenoid, and here we are taking soft iron. If we know that soft iron, there will be another thing is hard iron. Both are iron only. Soft iron doesn't mean like it is a softest material. That is, it is easily magnetized, and when we switch off the current, they can easily demagnetize, and that material is called as soft iron. Whereas hard iron is extremely hard to magnetize, and once if it is magnetized, extremely hard to demagnetize. So that acts as a permanent magnet, and soft iron acts as a temporary magnet. And we know that electromagnet is nothing but artificial magnet. Therefore we are taking here soft iron. Look at this diagram. Observe here a current carrying solenoid coil having rod inside, that is soft iron. For what? For better magnetic field lines. And the direction of magnetic field inside a solenoid, it is same as it is in the bar magnet. What we learned in the bar magnet, just recall. Outside the solenoid, magnetic field moves from north to south, and inside the solenoid, magnetic field lines are from south to north. Again, this part is also important. If they ask for 1 marks, you need to remember the direction, and remember it is same in both bar magnet as well as solenoid. Now let us solve in-text questions. The magnetic field in a given region is uniform. Draw a diagram to represent it. Understand the question. Here they are not asking directly whether it is circular loop or solenoid or bar magnet or straight conductor. They are given statement: the magnetic field in a given region is uniform. Draw a diagram to represent it. Now just recall where we studied uniform. Uniform and parallel lines comes under solenoid, right? Therefore here we need to draw magnetic field in solenoid. Next question. It is a MCQ. Choose the correct option. The magnetic field inside a long straight solenoid carrying current. The options are: first one is 0, second one is decreases as we move towards its end, third one is increases as we move towards its end, and the last option is it is the same at all the points. See, look at what is the statement given in the question. The magnetic field inside a long straight solenoid. So when we hear the term solenoid, remember the magnetic fields are uniform. with parallel lines, right? Therefore, the option D is our answer. It is same at all the points because magnetic field lines inside a solenoid are uniform. Therefore, magnetic field is same at all points. The question is, consider a circular loop of wire lying in the plane of the table. Let the current pass through the loop clockwise. Apply the right hand rule to find out the direction of the magnetic field inside and outside the loop. Reread the question again. Note down the given things. See here they are given the conductor is in circular loop. So imagine or recall magnetic field in circular loop and they are given that current pass through the clockwise. So these are the two given things and we need to find out magnetic field inside and outside the loop. They are given that a circular loop of wire lying in the plane of the table. Now just imagine it as a table or any cardboard sheet like that, how we did in circular loop activity. First, by looking at the explanation, we need to draw the diagram. Look at this diagram. In the question, they are given that correct direction of current is clockwise. So now we need to concentrate while writing the positive and negative terminal in this circuit. See, here I wrote positive this side and negative this side. Why I wrote positive terminal here? If it is our positive terminal, then current will flow from positive terminal, right? So current will start flow from this side of a loop. See, positive direction means, clockwise direction means which flow like this, right? Imagine the clock 1, 2, 3, 4 and here we have 12, so it will flow like this. In case if it is anti-clockwise, then it will, what happens? It will flow like this. Anti-clockwise means we need to interchange the signs. The plus should be here and the minus should be here. Since they are given only clockwise, we need to follow this. Now current start flow like this. Okay. So first thing is write all the direction how current flows. Now we need to find out magnetic field. So let us take on either side of a loop. Just write on the circles how we wrote in the circular loop. We'll get like this on both the sides. See, one more thing here, they are given in the question table. So table also nothing but it will like a sheet, right? So we need to just draw a simple schematic diagram. No need to draw table and all. Just we need to imagine we have a table here. So now current flows like this. Here it will flow like this. In the question they are told to apply right hand thumb rule. So just apply right hand thumb rule. Make an activity and see. If you want, just take one circular, any bangle or anything material and find out. See, now we are keep on in vertical way, but we need to take in horizontal way. When we take it in a horizontal way, we'll get exactly how it looks. So when we apply the right hand thumb rule, the magnetic field will flow like this, and that side it will flow like this. See, just look, we have a right hand thumb rule like this. When you go like this, we can't see, we'll get like this. So look at this, it's flowing towards like this. So observe my fingers, we'll get exactly same direction and same thing apply towards. Now this is our circuit diagram and magnetic field lines. Now what is the question? Inside and outside the loop, magnetic field. So this is inside the loop. Observe the direction. Inside the loop, we can say there are downward field lines. Observe this arrow mark. Now both the side we have downward field lines. And what happens outside? Outside we have upward field lines. So this is the answer. Write this diagram and later write down magnetic field. Inside the loop is downwards and outside the loop is upwards.